Now friends, the first algorithm that we will be learning is linear regression algorithm. Let's understand what we mean by linear regression algorithm. Let's say there is a variable y. Now this variable is dependent on a few other variables, say x1, x2, x3, up to xn. To simplify, let's say it depends on 3 variables, x1, x2, x3. Okay. Now what linear regression means is basically this variable y, when plotted against this set of variables, gives a linear pattern. What we mean by that? Let's say we draw a graph. To simplify it, we are drawing a 2D graph where this line represents, this horizontal line represents the x1, x2 and x3 variables, and the vertical line represents the y variable. Okay. Now if for any set of these numbers, say here, 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 like this, for any set of these numbers, if we plot y, it will generally give us a trend which is linear. It will be like this. Sort of like this, a linear pattern will form if we plot the x's alongside the y, right? So let us draw a line here. Let us draw the line here. Now if we take all these points and create a line which is best suiting for these points, to represent these points, that will be called the linear regression line, right? Now there are 2 types of linear regression basically. Let's say y is dependent on only one variable, which is x. In this case, this will be called a simple linear regression. On the other hand, the example that we have taken, let's say y is dependent on more than one variables, x1, x2, x3, like that. In a case like this, if y is said to be dependent on more than one variables, then this regression form will be called multiple linear regression. Multiple linear regression. The example that we have taken is basically a case of multiple linear regression where y is dependent on more than one variables, x1, x2, x3, right? It can be more than 3 variables also. And here we have represented it only with a 2D diagram, because if you go beyond 3D, you cannot represent it in a diagrammatic format. It's not comprehensible. It becomes n-dimensional space. So to simplify it, what we have done is we have reduced the x variables to one line only, and this has given us this 2D line basically. Now there is a term for these x features and there is a term for this y feature. What are those terms? Here we have clearly told that y depends on x1, x2 and x3, right? So here y is dependent, so y is called the dependent variable. Dependent variable. And these x1, x2, x3, these are called independent variables. x1, x2, x3, these are called independent variables. Okay. Y can also be called output, and x is also called features. Now one more question that can come in our mind is, how do we decide which line is basically going to be the best fitting line for these set of points? How do we decide that? How do we measure that? There are multiple ways of doing it. We will explore one of the ways, and it is one of the most popular ways also, my friend. Let's see that. Let us say we take one point in the features line. Let's say this point, right? Let me change the color here. We're taking this point to denote the features, the value of the features, right? This is a particular unique set of x1, x2 and x3. Now, we have already drawn the line. What we want to do is, we want to draw a vertical line now which meets this regression line, right? So this is the vertical line that can come here approximately. Okay. So let's say this point comes as our point on the line. So this is basically the prediction of our regression or the regression line, right? So we denote it by y hat. But the actual y, where is it? If you see the picture carefully in this case, you will find that the actual y is a little away from this. This is the actual y, right? So there is a little bit of a noise or error. So what we do is, we calculate this error, y minus y hat. This becomes the error. Now, if the actual y is below the line, then this y will be negative, right? For example, if we take this point, here if you draw the vertical line, you will find that the prediction is coming here, right? Here it is coming, but the actual y is here, right? So this is the y hat, this is the y in this case. Here it will be negative. In the case that we chose before, it is positive. Now to avoid this kind of a situation, what we do is, we square the errors. We take the square of the errors. Now there are multiple points and there will be therefore multiple errors. So we sum them all and we take an average of this. Okay. Our objective is to minimize this value. This value is what? This value is basically the average of the squares of the errors. Okay. Now, let's say this average of the squares of the errors is j. Our objective is minimizing this error, this value basically. Okay. So because there is a square here and we minimize it through use of calculus, we use a 2 here. Okay. For those who do not have any interest on differentiation and integration and all that, just we mean to say that when you use differentiation, when you differentiate a square number, you get a coefficient of 2. Just to nullify that, what we do is we use a 2 in the denominator. Now friends, this entire operation that we have done is having a term. This is called the cost function. So we will delve a little deeper into this a little later. Let us first do a simple linear regression practical with a simple data. It's a multiple linear regression that we are going to do hands-on right now. Okay, let's do it, friends. So friends, before we get into the practicals, I would like to dive a little deeper into the linear regression equation. So we have seen some graphical representations with simplified 2D figures, right, for multiple linear regression. But we are yet to explore how the equation looks like and how that equation is represented by the regression line itself. So let's do that. We will start with simple linear regression, SLR. So simple linear regression means y is dependent on one feature or one independent variable. Let's say that is x. So y is the dependent variable. In a simple linear regression, it is dependent on only one independent variable or one feature, which is here represented by x. Now, how would the linear regression equation for this simple linear regression look like? This will look something like this, friends. Y is equal to ax plus b. Here, a is basically the slope of the regression line and b is the intercept of the regression line. A can also be called the coefficient of the feature, and this is called the intercept. Now let us proceed to the graphical representation of it. So let's say this vertical line represents the y and this horizontal line represents the x. In our assumption, we are going to draw the line like this. This is our simple linear regression line, which is represented by this equation also. So let us now explore how are a, x, b and y represented in this graphical representation. So let's say this is the value of x we choose, just to understand what x, y, a and b mean in this graphical situation. So if this is the value of x we have chosen, this graph is saying that the corresponding value of y is here, or it means the corresponding value of y is here. This is the value of y. And where is this intercept b, my friends? It is this portion. This is the distance between the origin means where the x axis meets the y axis, the origin and the distance from this origin to the point of intersection between the line of simple linear regression, this is the line, and the y axis. So this intersection point of y axis and the regression line and the point of origin, the distance between these 2 points, this is the intercept or the b, right? Now where is this a represented, friends? Now we are seeing the slope of this line is something like this, right? So let's say the angle of this slope is theta. Now if we do a trigonometric operation on this theta, which is tan theta, tangent of theta, that is basically what a means. This is a trigonometric operation which basically decides the magnitude of the slope. Okay, so a is tangent of this angle theta, angle of slope theta. So now we know what a means, where y is, where x is and where b is, right? Now this is something we have done for a simple linear regression. Now let us try to understand how these things are represented in a multiple linear regression. MLR or a multiple linear regression is, we already know the definition, friends. Y or the dependent variable is dependent on multiple features or independent variables. Let's say x1, x2 and x3. How will the equation look like, friends? Let's say it will look like this. Y is equal to a1 x1 8 plus a2 x2 plus a3 x3 plus b. This is how this equation will look like. But there is a problem, friends. Here we will need a 4-dimensional space to represent this equation. So we have x1, we have x2, we have x3, we have y. So we will need a 4-dimensional space to actually reflect this properly, which is impossible, friends, because the maximum dimensionality that can be represented in pictorial format is a 3D space. So let's reduce the dimensionality a little bit. Let's say y is dependent on only x1 and x2. Now this will be represented by a 3D space. Let's say this is represented by the equation y is equal to a1 x1 plus a2 x2 plus b, right? This is the equation. Now how do we represent it in a 3D format? Let's see that. Let's say this is the vertical axis, which is represented by y. This is the horizontal axis. One of the features that is represented here, this is the x1, and this is the third dimension, which is x2, right? Now let's say the line goes something like this. It starts somewhere from here and goes like this. Now this line creates an angle with this axis also. This line creates an angle with this axis also. These angles, let's say they are theta 1 and theta 2, right? It's very difficult to understand in this way. We can separate them out. Let's say we just isolate y and x1, and here if we just do a projection of this line is basically a line in the 3D space, right? We need a projection of this line or a shadow of this line on the space which is two-dimensional space, which is represented by y and x1. This page, you can assume this page, right? So we do a projection of it and it comes something like this, let's say. Okay. Now this angle, let's say it's theta 1. Therefore, A1 will be equal to tan theta 1. This is the A1 that we are talking about. Okay. Again, let us separate out y and x2. Okay. So we are going to separate out this space. And this same line has a projection here also. So let's assume the projection looks like this. Now the projection of this basically is y and x2, right? Now the angle of slope here is theta 2, let's say. Therefore A2 is going to be represented as tan theta 2. Okay. So these two, A1 and A2, are our coefficients, right? Coefficients. And where is the intercept, my friends? Obviously it is this portion. This portion. The point of origin and the point of intersection of the regression line with y. Right? This is our intercept here in this case. So this is our intercept. And how do we measure the value of y, friends, in this case? So for example, we have chosen a certain value of x1 and x2, let's say. We have chosen this value for x2 and this value for x1. So how do we measure the value of y respectively, friends? Simply what we do is, we already have understood what is A2, A1 and B. How we measure is, we multiply A1 with x1, then we multiply A2 with x2, then we add B. So we add all these three terms and we end up with the value of y, the respective value of y, right? And how do we graphically locate this point y, friends? So in this line, where is the y? How do we locate that? Let's look at it. So let's say we do a projection of this multiple linear regression line on the x2, x1 plane, this plane, right? And the projection, the shadow of this multiple linear regression line on this x1, x2 plane comes somewhat like this, let's say. Now, x1 is here, x2 is here. Now what we do is, if we draw vertical line from axis x2 and axis x1 and try to join it to this projection of the multiple linear regression line, a very nice thing happens. What happens is, these vertical lines, a vertical line from axis of x2 and a vertical line from axis of x1, they meet, right? We have a point here, and this point, if we reverse project it on this line, we get our desired y. So this is how it happens. So we reverse project it on this point and we get our y. So basically the projection, this projection of multiple linear regression line is basically something like this, right? And for any of these points, there is a corresponding x1 and x2 combination which can be decided from this point that I am pointing right now. So you just need to draw a vertical line, vertical drop from here, and you just need to draw a vertical drop from here. You will get the corresponding x1 and x2s, right? So you can see this is a super complicated way of understanding things. So that's why what we were doing is, we were drawing a vertical axis and this axis was representing y, and for the set of features, whatever numbers they are, we did not pay separate attention to them. What we did is we drew a horizontal axis and said these are the set of features represented by capital X, because in modern times features may not only mean a number of features of 2 or 3 or 100, it may mean thousands or even millions. So especially in case of generative AIs, the number of features can go up till huge numbers. So this is a better way of understanding things, because 2D is a safer way of understanding how the linear regression works. So friends, now we will move into the practicals. So friends, we have reached our Jupyter notebook. The data that we are going to use is basically this data. What we can see here is there are 3 columns: experience, YGPA and salary. The salary here is the dependent variable, and experience and YGPA are basically the independent variables. So what we are trying to mean here is the experience and YGPA, that is the score and the experience of a person, basically determines what their salary will be. Okay, so this data we are going to use to do a linear regression, and specifically a multiple linear regression. Why a multiple linear regression? Because the number of independent variables is more than 1. Here there are 2 independent variables, experience and YGPA. So let's get started, friends. First, to use the databases, we need something called the pandas. Import pandas as PD. Then to work with the numbers, we need something called NumPy. Pandas and NumPy, these are basically libraries which help us do multiple operations. Pandas helps us in working with databases. NumPy helps us in working with the numbers or the values in those databases, right? So shift enter, and these 2 are imported. Now we have to import the data also here. We create a database where we will import the Excel sheet that we are talking about. So this is, let us call it df. df is equal to pd.read CSV. Why CSV? Because the file format that we opened was in CSV format. The name of the file was salary data csv.csv. Now let us see if we are able to view it. Yes, we are able to view it. Now to do the regression, there are 2 aspects basically. One is the y, which is the output, and another is the set of all the x, that is the features. Now we have to separate this data of experience, YGPA and salary into the set of x, that is the features, and the output. So let us do that. X is equal to df dot, we need the first 2 columns. So for that we use a command called iloc. Iloc, first we need all the rows, then we need first 2 columns, right? Now how do we select all the rows? We start with the first index and then we look at the last index number, it is 1374. What we do is we write 1375 here. So if we write like this, it will select all the rows. Similarly for the columns, if we want the first 2 columns, we write 0 till 2. So we want 0 and 1. So for that we have to write 0 colon 2. Okay. Let's see if we have done the right thing. See. Now what would have happened if instead of 1375 we would have written the right index number, right? 1374, or we would have written 0 and 1 here. Let's see that also. Instead of 1375, one might think, why 1375? We should just write 1374, and here we just need 0 and 1, so we should write 0 to 1. Now what happens here is this. See, the command works like this, that the number you put, it automatically reduces it to 1 and then selects that range. So you have to add 1 and then select the range, right? So here just to confirm, see, the last index number is 1373, but the last index actually is 1374, not 1373. So one less has been selected. Similarly, in terms of columns, only the first column has been selected. The second one is missing here. So if we do it 1375 and 0 to 2, we get the right selection, right? So that's what we have done exactly. For y, we need the last column and we need all the rows. So what we'll write? df.ilog 0 to 1375 and then 2:3. Because we need column number 2, we write 2:3. See friends, here we have got the last column. Okay. Now we are ready to do the regression. Now generally when we are doing machine learning, we divide the data set into training set and testing set. What we mean by training set and testing set? Basically, we train the model, the linear regression model, in a part of the data, and then in another part of the data, we test to see how good the predictions are working based on that model, right? We create a good model or the linear regression model on the training data. Then we use that model to predict values and then match to see whether the results are coming good or bad. Okay. So here we will be dividing x and y into training and test set data. So for that we will import a module called the train test split from sklearn dot model selection import train test split. So we do not remember these things. If you just forget it, you can just Google it, import train test split, where from, you will find it easily. Okay. Now we are going to use train test split and create the training and testing data. So x train, x test, these will be two splitting of the x, right? And for the y also we'll be splitting it into y train and y test. Y train, y test. This will be coming from train test split. The source of the data for x train and x test is x. The source of the data for y train and y test is y. Then we will decide on the test size. The test size is basically proportionately much less than the training data size. Okay. So here let us say 25% is the data we will be keeping for testing of the model. The rest of the data will be using for training. So here we write test size is equal to 25% or 0.25. Then we use something called random state, right? Random state is equal to 42. Now what do we mean by random state is equal to 42? Now what do we mean by random state is equal to 42? Basically friends, the random state and the fixing of a number of the random state basically ensures that whenever you split the data, the same kind of splitting happens. For example, if you are going to split the data with mentioning a random state of 42, then if you split it 7 times or 17 times or 70 times, the splitting will happen in identical fashions. That means never will it happen that the data in some iteration was in x train and then it came into x test, some data point. It will always be identically split if you use the same random state and obviously the same test size. Okay. So let us execute it, shift enter. It is done. Let's see what is the x train coming at. You see here friends, we have 1031 rows and 2 columns. Now it should be 75% of the total data, right? So there should be 1031 by 1375 should be 75%. Let's see, 1031 by 1375. Yeah, it's almost 75%, 74.98. Similarly, X test is coming to 344 rows. 344 divided by 1375, this comes to again 25%, 0.25, right? So the splitting is okay. Now the splitting is done. We have to now create the model. To create the model, we have to import the linear regression module. So from sklearn.linear model, import linear regression. We are going to use it. We are going to use the linear regression model. For that, we write linreg is equal to linear regression. Now it is usable. Now in this linear regression model, we'll be fitting the data that we have, and the data will be the training data that we have. So what this will do is help the model create a linear regression line for future predictions. Okay, so linear regression linreg.fit x train y train. Okay, so we use the output and the input features to train the model and create a regression line which will be able to predict salaries in the future if experience and YGP are given, right? So we press shift enter, linreg. Now this shows that the linear regression model is ready. Now we will be predicting. So for predicting, what we do is linreg dot predict. Now for prediction, we will just need the input features. The output will be predictive in nature. Okay, so we used X test. Okay, now you see a bunch of salaries have been predicted. We save it in y hat. Y hat is basically the y predicted as per our theory, right? So we save it in y hat. We could write y pred also here. Y predict, y pred, y hat, things like that. Any name you can give. Now we would be doing one thing. We would be trying to understand how good the prediction is. So to do that, we need something called the R2 score. R2 score, what that is, we will get into it in a very short while. But one thing is, the closer to 1 it is, the better it is. It ranges, say, from, it can be 30%, it can be 40%, that is 0.3, 0.4, 0.5, 0.8, 0.9, 0.95. All these numbers are possible for R2 score, and the higher the number is, that is, the closer the number is to 1, the better the performance is. It's basically a decimal representation of a percentage. So R2 score is 0.85, means the performance is 85% accurate. You can say in one sense that way. Okay, so let's see what the R2 score of this is. From sklearn.metrics, sklearn, import R2 score. R2 score we will find out by comparing y hat and y test, right? So y test is basically the actual values of the salaries, and y hat is what the predictive model has predicted those values should be. Now how accurate this is, we will get to know. So R2 square is coming 0.98146%, that is, it is somewhere around 9.146%, which is very good. Now we try to understand what this R2 score is, friends. For that, we will do one thing. We will just go to this Excel data or the CSV data and figure out what R2 score basically is. Okay, let's first visualize the y test data. You can see this is how the data has been split, right? So it's 26,177 like this, 6,530, 7530, 19618, 27025. We'll be just taking a sample of 5 data points and comparing the y hat and y test and measuring the R2 score for them. Now the y hat, we convert it into a data frame. PD dot data frame y hat. So friends, here we have we can see that this has been turned into a data frame, but the column name is 0. So we want to change it to, let's say, y hat itself. So what we do is just this, y hat dot rename columns, and we have to change 0 to y hat, right? In place equal to true. So this changes the data in the actual database. Okay. Now let us see, y hat is coming to be this. Okay. Now what we are doing is, we were basically trying to understand the R2 score on a practical hands-on basis, right? So we copy this one and paste it in the Excel. So here side by side we have y and y hat. Now from this, how do we get the R2 score? For that, let us go to the theory part. Let's say we have a regression like this. The vertical axis, which represents the y, and the horizontal axis for the set of x features, right? And the plot is something like this. It's a linear trend plot. Now let us draw a regression line against it. We can easily draw something like this. Right? Now, to find R2 score, we need to understand a few things. Let's see what are these. If we take one of the set of features, let's say this one, and we try to predict the respective y value, it should come somewhere here, right? Now according to theory, this point is our y hat, one of the y hats, and let's say there are total m data points, right? This is the first one that we are doing. So here this is the y hat, but one thing you will see, guys, the real y seems to be here, right? The real y seems to be here. So there is a distance between the two. What we do is, we measure this distance. Let's say this is the ith data point. So this is the ith data point and this is the error, right? Error for the ith data point. Again, for another one, let's say this data point. Let's say this is the jth data point. We predict the y hat. The y hat seems to be here, but the real y, we can say this one. So again, there is a distance between the two, right? So for the jth iteration, we again measure y minus y hat. This is the y hat, friends, and this is the y. So for all these cases, that is 1, 2, 3, 4, ith, jth, up till all the m data points, we calculate the errors. till m. And what we do is we square each of these values. We square each of these values. Okay. Now, the sum of these square values, we call it sum of squared error. Sum of squared errors. Okay. Similarly, we also calculate one more thing. We add up all the real y's, the actual y's, y1, y2, y3, yi, yj, yk, like this, all the m y's we add up. We add them up, right? And we divide it by the number of data points that we have. So from here we get something called the y mean or the y bar. This is the y mean, right, or the y bar. So here also what we do is, from each of these y's, from all these data points till the last data point, we subtract the y bar or the y mean. So from the first one we do this, from the second one we do this, from the third one we do this, till m we do this, and again we square each of them, and we sum them up. This sum we call the sum of squared total. Sum of squared total. And by dividing sum of squared error with sum of squared total, we get something like the degree of error, right? This is a measure of the degree of error present in the data or in the regression. Now, if we do 1 minus sum of squared error by sum of squared total, we get the degree of accuracy. Now, this total gives us the degree of accuracy or degree of goodness of fit. This is what we call the R2 score. Okay, and this is expressed in another way, friends. This is also expressed as, I can write it here, sum of squared regression by sum of squared total is equal to 1 minus sum of squared error by sum of squared total. So one new term we learn is sum of squared regression. Sum of squared regression, from this expression we can actually derive it as sum of squared regression is equal to SST minus SSE, and sum of squared regression by sum of squared total, this is R2 score. Okay. Now let us go back to the Excel sheet and perform these calculations in the actual sample or small sample that we have taken up, right? So first what we do is we try to find sum of squared error. Then what we do is we try to find sum of squared total. Then we divide the two and we subtract it from 1 to get R2 score. So first, for sum of squared error, what we need to find is y minus y hat and the square of it. So this has to be squared, right? So we do that. Y minus y hat whole square. So this is the first number that we have got. Now we do it for every number. Okay. And the sum of squared error The sum of squared error, we get it by summing these numbers up. Sum of these numbers is basically the sum of squared error. Now for this one, we need to do y minus y mean or y bar, y mean squared, right? Okay. So y minus average of these numbers. We have to square this. Okay, let us find the average separately. So we have got our y mean. This is the y mean, right? So here what we do is we do y minus the y mean, which is 17376, 17376, and we also square it. So we do it for every number here, right? Then if we do a sum of it, if we do a sum of this, we get the sum of squared total, right? Sum of this. Now what we do is we find out 1 minus SSE by SST, sum of squared error, sum of squared total, right? 1 minus sum of squared error by sum of squared total. This is equal to 1 minus sum of squared error is this divided by sum of squared total, which is this. This is our R2 score. For this small sample, this number is coming to be our R2 score, okay? Because this entire operation that we did is basically what R2 score is doing for the entire test database that we provided it. So here what is happening is this R2 score is basically doing this operation for the entire dataset of 344 rows, right? The test data if you see, it is 344 rows. So it is taking the test data and the y head data, which is here, you can see it here, and it is doing the same operations with these two databases and providing us a number. This number is 98.146%. In our small database, luckily we were getting a higher accuracy. So we are getting 99.0723% kind of figure, okay? Now friends, in the regression that we did just now, there was one output variable, right, which was y, and there were multiple features x1, x2, x3 like that. So this kind of a regression, as we already know, is basically a multiple linear regression, right? Now when a data is designed in the form of a multiple linear regression, that data has to follow certain rules or certain assumptions. Otherwise, even if we do a regression and the results are good, the data itself is invalid if these assumptions are violated by the data. So let's see what those assumptions are. We have written it here. Let's try to understand them one by one. Assumption number 1. The relationship between the dependent variable and the independent variable is linear. Quite obvious, friends. So let's say there is a set of features xa, xb and xc, and the y is related to it, and the data form is something like this. So here you can clearly see, if we draw a pattern, the pattern that suits this is mostly like this. It's not a straight line, right? If we try to force a straight line like this, say something like this, we already know intuitively that this is not going to work. The pattern is not this, the pattern is the green one, right? So this is basically a violation of assumption 1, which says the relationship between the dependent variable and the independent variables has to be linear. Okay, so what should be the ideal pattern here? It should be something like this: y and x1, x2, x3 set of features. The pattern has to be something like this. Now we see a much more clearer pattern, that it is a linear trend. Something like this it will be, right? Now we move on to the assumption or rule number 2. The independent variables are not random. The independent variables are not random. We'll try to understand what that is in just a while, which implies they are fixed and known and probably chosen based on some hypothesis or fundamental. There is no exact linear relationship among the independent variables or combinations of independent variables. Okay, what do we mean by this? Let's take our example where y is dependent on x1, x2 and x3, right? So what it is saying is, these x1, x2 and x3 are not random. They have a reason to be there. For example, we predicted salary based on some logical features, right, which was experience and score in their college grades. There can be other features also in some other database, but these two are logically related to this. These are not randomly chosen or something. And experience and score, they do not have any linear relationship between them. Basically, the assumption says, if we find that experience and score are having a linear relationship between them, then it will be a problem. Then we have to validate the data. This has to be corrected, or the data has to be rejected, basically. So what it is saying is, let's say if we draw a graph between, say, x1 and x2, there will be no linear pattern that will be found. It will be very haphazard kind of a arrangement if the data has to be ideal. If the data is not ideal, then if we plot x1 and x2, say, and if it comes like this, then it is a violation of assumption 2. That is, there is no exact relation among the independent variables or combination of independent variables. This part is being violated here, right? And these here, this example or the regression practical that we did, this is basically itself proves that when we are choosing an output and we are choosing the dependent variables, the independent variables are not randomly chosen. They are chosen for a reason. They are not random, right? So this is basically the assumption number 2. Then we move on to the next assumption, which is number 3, and it is the expected value of error term given a set of independent variables is 0. Now, what is essentially being meant by this? Let us dive deep into it. So here what is meant is the expected value of the error term given a set of independent variables is 0. Let us draw our linear regression first. This is the y-axis, this is the features axis, okay, right? Now let's say the plot looks like this. The actual values of y have generated a plot like this. Now friends, what this assumption is saying, the error values, if we sum them up, they will be expected to be 0. Why is that? Let's say we draw a regression line and we say this is the line that we choose, right, like this. Now do we see any problem with this line, friends? The problem is very clear. Most of the things are most of the outputs are below the line that we have chosen. Now what will happen in this case is, basically, let's say we choose this point for the features, right? We have chosen this point and we are going to predict y, right? So this will be the y hat. This will be the y hat, and the actual y will be below this. Again we choose another point. We choose this point. here again y hat will be here and the actual y will be here, right? Again we choose another point. The y will be somewhere here while the actual y will be here, or say here, like this. There cannot be two outputs. This is basically two separate outputs in space. Because of the closeness they are looking separate. So let us say this will be this. So in most cases what is happening is y hat is becoming greater than y, right? What will happen is the sum, if we do y minus y hat for all of these values, the sum of all these will tend to be negative. This will not be 0 because most of them are below, right? Let's look at a second case. The second case is, let's say we choose this kind of a line. Okay, what is the problem? It is again very clear. This kind of a regression line, if we choose, let's say we choose this point, the y predicted on the y hat will be here and the actual y will be somewhere here. Again choose another one, let's say we choose it somewhere around here, the actual y is here. So like this, if we do another one, so let's say this one we choose, again if we draw a vertical line, the predicted y hat will be here while the actual y is here. So what we see is the y minus y hat, if we sum them, it will tend to be positive and it will not be close to 0. But if we choose the best fit line, what will happen? Let's see. Let's say we choose this line. This line we have chosen. Now what happens is some of the points come below, some of the points come above, some of the points are near and below, some of the points are near and above, some of the points are far and above, some of the points are far and below, like this one, right? So they even out, somewhere they even out. So here what happens is the sum of y minus y hat becomes very close to 0. So for the best fit line, and if you are doing a multiple regression, the expected value of the error term given a set of independent variables is 0. This is what we mean by this assumption. If we have forgotten to choose it, then there is some problem either with the data points, maybe they are not linear, or we have not chosen the best fit line, right? That is the case. Now we go to the fourth assumption. The fourth assumption is, here also it is mentioned, you can cross check if it is the same thing. The variance of error term is the same for all observations. The variance of error terms is same for all observations. What do we mean by this? Let's look at it closely, friends. What we'll do is simply draw another regression plot. So these are our set of features, capital X. This is again the output, which is y, or the dependent variable. Let's say the plot looks like this. Again, it's a linear plot only, like this, right? Coming something like this. Now let's say we have found out the best fit line, which goes something like this, right? We have found out the best fit line, and now we will calculate and measure each of the error terms and find out the variance, right? What is the variance? Variance is basically, let's say if we take this set of features, we draw this. This is basically the y, and the predicted value which is on the line, regression line, this is the y hat. We do it for each and every data point, and we calculate y minus y hat, then we square them and we sum them and we take out their average. Let's say there are m data points, so the variance is basically average of this. What we do is we actually do m minus 1, statistically speaking. Why we do that, we will get into it when we discuss statistics, friends. This is not the scope here, but for variance it is basically the case, the number of examples minus 1, or 1 degree of freedom is reduced basically. So coming back to the variance, so this is basically the average of all the errors squared. This is basically the variance. Now what this assumption is saying is basically the variance of the error term is the same for all observations. So let's say we split this data. from here. Now, if we take the variance of this set and compare it with this set, then we will find that the variances of both the sides, let us say this is the side A and this is the side B, then the variance of the side A will be very much close to the variance of the side B. If we measure them separately, basically, instead of finding out the total variance, we separate this data and find out variance of each segment. In that case also, what will happen is we'll discover that the variance are the same in an ideal case, that is if the data has to be valid. Okay. Now there is a term for this, friends. If the assumption is held, then the data is called homoscedastic. If this is violated, then it is called heteroscedastic. So let's say we have a data like this. Basically we have the first segment, we have data points like this, right? After some time, what happens is we get data points like this, right? Now we can still draw a best fit line for this, and the sum of the errors will still be 0, because you can see if it's not perfectly here drawn with the middle, but if I draw it a little better, we can still draw this linear regression line or the best fit line, and the sum of the errors, if you find out, you will find that this assumption is held. The sum of the errors is coming very close to 0. But there is a problem. If you just segment the data here, then the variance, if you calculate this one and if you calculate this variance separately, then let's say this is A and this is B, then variance of A will be surely much less than variance of B, or generally speaking, variance of A will be not at all equal to variance of B. This is a violation of this factor, homoscedasticity. Okay. So this kind of a data will be called heteroscedastic. So this is homoscedastic with a C. So this data will be called an heteroscedastic data, and the phenomenon is called heteroscedasticity, right? So here the phenomenon is called homoscedasticity. The assumption itself is termed as homoscedasticity. Friends, now we come to the fifth assumption. The error term is uncorrelated across all sets of observations. So let's say we plot the horizontal axis. Let's say we plot the horizontal axis with all the observations. As we said, we had m data points, so we had m observations, right? And on the vertical axis, we draw all the errors, right? Errors. And here are the observations. These are basically the y's, okay? Now, what this assumption says is the error term is uncorrelated across all sets of observations. So this will give us a very random and haphazard scattered kind of database like this. Okay. So it will be more or less like this, equally distributed in all spaces. Now, how the violation can happen? The violation can happen when the distribution takes certain patterns. What kind of patterns? Very easily we can understand this, guys. If the pattern is looking like this, let's say like this, or if the pattern is looking like this. So in either of these cases, you can see there is a pattern formation. Here it is more like a linear kind of a formation, right? And here it is more like a exponential kind of a J-curve kind of a formation, right? So both these cases violate the assumption, and the data is rendered invalid in either of the cases. So this assumption has to hold. The error term is uncorrelated across observation. Across observation means all the observations taken together, right? This has to include all the data points taken together. That is, if there are m data points are taken together. Okay guys, now we move on to the sixth assumption. So As you can see, the error term is distributed normally. Now, what is a normal distribution? Basically, a normal distribution is a distribution where if you plot with 0 in the middle, if you plot on either side, the boundary of the plot looks somewhat like this. So, what I am trying to say is, if you like, this is the horizontal axis and the 0 is here, not on the corner, it is here, and if you plot the errors, in this case error term we are talking about, right? So, this is basically the error. This is basically the frequency of the value that is chosen here. So, let us say this point is chosen, the frequency of this point will be here, let us say here, okay. If you choose this point, the frequency will come down, it will come down to somewhere here. So, most of the values or 50% of the values will be within, say, one standard deviation. We will get into this complication later, but most of the values will concentrate around the 0. The further we go from 0 in terms of the error value, let us say we plot something here, the thing will come down further, like it will be here. Then if we choose this value of error, the frequency is here. So, what do you mean by frequency, guys? Frequency is basically the number of times this value has occurred, the number of times this value has occurred. Okay, we will not get into the values magnitudes, but it is like increasing away from 0, it is going towards infinity, and this is also going away to positive infinity. This is negative, this is positive infinity. So, we choose this point, this point, this point, this point. The further we go from the mean, that is which is 0, the frequency of occurrence of those values become less and less and less, right? Frequency means the number of times that value comes, and the distribution obviously looks normal or normalish, at least it is something like this, right? There are few other features of a perfect normal distribution, but this is the general definition basically. So, nearby 0 the maximum number of values will be there. So, the frequency is highest between these points, like from here to here. Then as we go into the extremities further and further down, the frequency of occurrence of those values of errors come down. I hope I am able to communicate. So, this is mostly about the errors. Now, we will also take a glance at the error violations and the terms used for it, right? So, these are the violations and the terms for it. First is heteroscedasticity, then there is serial correlation, and then there is multicollinearity. Let us look at them one by one. First, we look at heteroscedasticity. We have already touched upon it. The variance of the error terms varies across observations. So, again we will touch upon this one. We have already done that, but again let us do it. So, heteroscedasticity basically means you have a data point like this. This is going like this, and then suddenly the data spreads like this. And if someone draws a line here, they can actually draw a best fit line here. And if you separate the zones from the low variance and the high variance, you will see that this area has clearly low variance and this area is completely different in terms of their terms behavior. It has become much more spread, much more volatile and all that. Okay. So, this is the y and this is the x, set of x. So, if you measure the errors in this area, the variance will be much more. This is called heteroscedasticity, right? So, error variance, let us say this is zone A, zone B. Error variance in zone A is not at all identical to error variance in zone B. So, this is one of the violations. Serial correlation. Error terms are correlated across observations. Again, we touched upon this one also. Let us say we have this kind of a pattern. We plot the y in the horizontal axis and the errors in the vertical axis, and we get this kind of a plot. Let us say this kind of a plot. So, the errors are clearly correlated with respect to the y. With the y, there is a clear relation here which we can establish in the form of a linear equation maybe. This is a violation. This is called serial correlation. Multicollinearity. Two or more independent variables are correlated among themselves. This again we had touched these also, that there should be no relation or linear relation between the variables. This is what is being mentioned here. If there is a linear relation, let's say what we did is we assume that y is dependent on x1, x2 and x3. Now let's say we plot, so let us border this one so that it does not get mixed up. This is another one. Now we are doing the third violation. So here it is like this. Let's say we plot x1 with one of the other variables, and suddenly we find that the plot is like this. This is multicollinearity, that the independent variables have a relation between themselves, right? So this is a violation of the condition that there should be no linear relation between the independent variables, and this is called multicollinearity. So this is about the violations. We also have to look at how to measure this in Python itself. So that we'll do in the practical section. Now let us check whether these assumptions that we spoke about in the theory part actually do hold in our practical database or not, right? So to visualize whether these data follow our assumptions, what we have to do is we have to import something called Seaborn. Import Seaborn as SNS. This is basically a plotting module. We can plot different kinds of graphs with it. Also, as an alternative, we can import matplotlib.pyplot as PLT. This is also another plotting module. It will let us plot different kinds of graphs. Now the first assumption was the relationship between dependent variable and the independent variable is linear. So let us see if we have been able to create an equation or not, okay? A linear equation or not. So for that, what we do is simply we write linreg dot coefficients. We get a couple of numbers. Also we write linreg dot intercept. We get another number. So what are these coefficients, friends? We had two features, right? One was experience and one was YGPA. Let us revisit the data initially. One was experience and one was YGPA. So this coefficient part, this coefficient data part, what it is saying is, you have a linear equation, you have generated a linear equation, and the equation has these coefficients for your input features or the independent variables. And what is the intercept saying, friends? So apart from the coefficients to the input features, we have another intercept feature, which is basically the point where the line meets the vertical axis. So let's say, let us go to the framework once again. This was the regression, right? This is the y and this is the set of x. We are simplifying it into 2D basically. So what this is saying is, you have a line like this. Here the line is not passing through the origin, that is, it is not passing through where y and x meet, it is passing through some distance, right? It can be either this side or it can be below this also, right? So it can be on the negative side also. If it is from the negative side, the intercept will be negative, and if it is on the positive side, the intercept will be positive. In our case, the intercept was most probably negative, so line will be most probably like this, and the coefficients obviously will give you the measure of the slope. the slope at which this is going, right? This one, this slope, the degree of the slope. So let us write it in equation format itself. Now print our linear regression equation looks like this. Now we write the equation. Print f string. First we write the y variable, then we write the intercept, then the coefficient of experience. So we write here experience, then we write the coefficient of YGPA, then we write YGPA, and this is the end of our equation. Now we put the values here. So here we write salary is equal to, first one is linreg dot intercept. Here you can see this is basically an array and with one element. So we just write 0 here to get the first element, right? Now for the second one, we have the coefficient of the experience, right? So this is experience, and here we write linreg dot coefficient. See here there are two brackets, so this means it's an array within an array, right? So what we write here is 0, 0. So the first 0 basically captures the entire array, and the second 0 captures the first value within this array, right? And for the second one we use the same thing, linreg coefficient 0, 0, or the only change we make is instead of 0, the second 0 we use 1. So the first 0 captures this entire array, and the second 1 value captures the second value of this array, right? Now we press shift enter, and this is the equation that is there. Our linear regression equation looks like this. Salary is equal to minus 204 point something plus 1194 point something into experience plus 432 point YGPA. So we have got our linear regression. So this is the first assumption we have gone through. Now we will look at whether we have satisfied our second assumption or not. The independent variables are not random, which implies they are fixed and known and probably based on some hypothesis. There is no exact linear relation among the independent variables. Okay, so there are two independent variables. We just have to check whether they are linearly related or not. So for that, what we do is we use something called the pair plot. SNS dot pair plot, and for that we use the data of x. Now you see here what happens. We have a plot which is plotting experience with YGPA. We have another plot which is plotting experience with YGPA in the reverse direction axis wise. So you can see here, friends, there is no relation here. This is a square pattern that has formed, random square pattern. There are no patterns here, right? With this kind of value, there is no slanting array of dots or like non-linear curve of dots here. This is just a linear scatter. Okay, we can use matplotlib also for this. So plt dot scatter x experience with x YGPA. Again you can see the same kind of pattern is formed. There is no linear or non-linear curve that is forming here. It's a perfect data in this sense. Now first let us calculate the errors. So error is equal to y minus y hat or y test minus y hat. Y test dot values minus y hat dot values. Let us see. First we convert this into data frame. So error is equal to pd dot data frame error. Okay. The variance of the error term is same for all observations. Okay. So for this what we need to do is we need to find out the y minus y hat whole square and then plot it against y to see whether there is any pattern formation or not. Okay. So error squared is equal to error into error. Now you have this. You see, these are the values that we are getting, right? We again rename the column, rename columns is equal to, we rename 0 to error squared, and we say in place is equal to true. So we have changed it, right? Now what we have to do is we have to plot this error squared with respect to the observations, that is the y. So for this what we do is we use PLT and we do a scatter plot. So on the x-axis what we do is we put the observations, that is the y test or the salaries. And for the vertical axis, the y-axis, we use the error squared. Let's see. Again, you can see friends, there is no real pattern, it's just a distribution, right? Now near the 0, there is a concentration of values, and as we go away from 0, the values become scarcer. So this is the error term is uncorrelated across observations. So this is the error term is uncorrelated across all sets of observations. This is also defined by this plot only, right? There is no particular change of distribution or any curve here which is showing up. So this is fine. Now we go into the sixth assumption, which is the error term is distributed normally. Okay. Let's see. For this we do a histogram plot, right? So SNS dot hist plot, and this is for the error. So this is a kind of uniform distribution that we have, but it's fine because we have synthesized the data in this way. Now we will look at the violations of the error terms. So now we will look at the violations of heteroscedasticity, multicollinearity and serial correlation, if they exist or not. First, what we do is we check for heteroscedasticity. For this, what we do is we do a scatter plot between the error and the y, right? So PLT dot scatter y test compared with error. See here, it's a completely squarish distribution. There is no kind of this thing, right? So this data basically represents that there is no heteroscedasticity. So the data is homoscedastic. Data is homoscedastic. Then what we do is we check for serial correlation. Serial correlation means errors and observations to show some kind of pattern. So for that also we do the same thing. This scatter plot itself shows it, Again we do it. There is no pattern formation here. It's completely uniformly square distribution is there. So the data is not serially correlated, right? Now we have to check for multicollinearity. Multicollinearity means the x variables, that is the features, are correlated between themselves. So we have two x features, experience and y GPA. We do a plot against each of them to see whether they are correlated. So SNS dot pair plot, or let's say PLT dot scatter x experience and x YGPA, right? Okay, experience. We have already done this actually. So here you can see again a square distribution, there is no pattern here. So the data has no multicollinearity. So that's it, my friends. Next we will move on to the logistic regression. Let me remind you, there are more complex ways of measuring for and correcting for these problems, like Dickey-Fuller test, Brosh-Pagan test, White test. All these things are there. We will take some other scope for discussing them. For now we will stop here and we will go into logistic regression and in-depth study of what a cost function is. Thank you.